Hello viewer, this is Elim TV. Welcome to FORM2 Physics Lesson 4, and the topic is magnetism. Today our discussion revolves around magnetic field patterns, and I'm going to be your teacher, Benjamin K. Makanda. So enjoy the lesson. Before we start our lesson, you can send your comments, questions on our SMS number 40007. You can also use our Facebook page, Elim TV, and also follow us on Twitter at ElimTV_KE. So to begin our lesson, let's look at the specific objectives. By the end of this lesson, the learner should be able to describe patterns of magnetic fields. So this is our core objective that we have to achieve: describe patterns of magnetic field. Lesson preview. Review of lesson 3. In lesson 3, we looked at the various ways of making a material a magnet, and we also looked at how magnetic lines of force emanate, how they move, and all that. So today, what we want now to look at how we can be able to describe the patterns of magnetic field. Description of the patterns of magnetic field, after which we are going to look at some questions that can help us understand our discussion even better. That is your assignment for the day. So we begin our discussion by looking at magnetic field patterns. And what are the magnetic field patterns? The direction of magnetic field line is defined to be the direction in which the north end of compass needle points. So we have here a magnetic field line. A magnetic field line is a line of force through which a magnetic field is created. Magnetic field is actually created. So we define magnetic field lines as the direction in which the north pole end of a compass needle points when placed in that particular direction. So if you take a north pole of any given magnet or a compass needle and you place on a magnetic field line, then that direction towards which the needle is going to point detects or explains what a magnetic field line is. So the other thing about magnetic field line is that the magnetic field line is traditionally called the B field. So to help us understand this, we have these diagrams that can help us understand the magnetic field patterns. So how do the magnetic field lines move? They always move from the north pole to the south pole. In the first diagram A, you note that the compass needle points away from the north pole. So the compass needle points away from the north pole, and this one tells us that the magnetic fields or the magnetic lines of force, they move from the north pole to the south pole. So this now can be helped to explain diagram B, where now we use the arrow pointing away from the north pole and getting into the south pole. That one still tells us that is the magnetic line of force. So the line of force moving from the north pole to the south pole. Now, we have a line of force and we have a magnetic field. Two terms here: line of force and magnetic field around the magnet. So let's differentiate them. Magnetic field is the area around a magnet where the magnetic force is experienced. Any area around a magnet where magnetic force is experienced, then that space or area is what we call the magnetic field. Now, the magnetic field line refers to the direction towards which the north pole of a magnet points or will travel if placed on that particular path. So there are two areas here. Magnetic line of force is the path, while the field is the area or space around a magnet where the influence of a magnet is felt. And we are saying the magnetic lines of force, they move from north pole and then to the south pole. And then the diagrams are here to help us understand that. The properties of magnetic field is the next thing we have to discuss. The direction of the magnetic field is tangent to the field line at any point in the space. So when you want to note the direction of the magnetic field, it forms a tangent to the field line at any point in that particular space. Tangent meaning that something like an angle. We have a curve, therefore it has to form a tangent. So that's the first property about the magnetic field. A small compass will point in the direction of the field line. So if you take a small compass and you place on the magnetic field, then it is going to point in the direction of the magnetic field line. And later on, as we're going to see, the magnetic field line actually points away from the North Pole. Still on the properties of magnetic field, this again is what we can say. The strength of the magnetic field is proportional to the closeness of the lines. It is exactly proportional to the number of lines per unit area perpendicular to the lines. This is called the areal or the areal density. Now, if you want to determine the strength of the magnetic field, then the intensity of the magnetic lines of force, when they are too close, they are concentrated, then the magnetic field is very strong. And when they are scattered, then the magnetic field is weak at that particular point. And that concept is what we call the areal density, the density of the lines around that particular point. So the point here, the strength of the field is proportional to the closeness of the lines, actually means that when the lines of force are close together, then the strength or the field is very strong. And when the lines are scattered, then the fields are weak. Moving on, still on the properties of magnetic field, magnetic fields can never cross, meaning that the field is unique at any point in space. Any magnetic line of force cannot cross, they don't cross. So meaning that any line has its own uniqueness, it has a unique property, so they don't cross. From the North Pole, they will just move directly to the South Pole without crossing, and they make them to be very unique. So if you are drawing the magnetic field around any given magnet, then it's a mistake for you to cross the lines of force because they don't cross. This property is very, very important, especially when you are drawing the magnetic lines, the magnetic field around any given magnet. The other property about magnetic field is that magnetic field lines are continuous, forming closed loops without beginning or end. They go from the North Pole to the South Pole, and we have emphasized on this. They form continuous loop without beginning or end. You may not tell whether they are stopping or it's a continuous kind of thing from the diagram that we're going just to look at. They go from the North Pole to the end to the South Pole. So they move from the North Pole to the South Pole. So if you draw a magnetic field around a magnet, let's say a bar magnet, and you draw the field moving from the South Pole to the North Pole, definitely you are wrong. Because the lines of force move from the North Pole to the South Pole. This is very, very important for you if you want to draw the diagram showing how the fields move. They move from the North Pole to the South Pole. Now, to help us understand, let's have a look at this diagram here. In the first place, we want to look at the magnetic field pattern due to a bar magnet. How does the magnetic field pattern look like in a bar magnet? So this is what we have. We have a bar magnet here, the magnetic field pattern due to a bar magnet. Still, they move from the North Pole to the South Pole. We have the first field here, which is straight, and as the field continue to move, they keep on curving. So that's how the field moves in a bar magnet. That's how you are able to actually explain or draw the magnetic field pattern due to a bar magnet like the one we have here. The other diagram that can help us understand this is this one here. Yeah, the magnetic field pattern due to a bar magnet still. So they are moving still from the North Pole to the South Pole, North Pole to the South Pole, North Pole to the South Pole. Now, if you have opposite poles of the bar magnet placed side by side, what happens at the beginning? The line of force moves from the North Pole to the South Pole, and then as they continue moving, since we have a force that exists between one line of force and the other, then they start forming a loop. Actually, they bulge outward. So that bulging outward shows that they are forming something like a ring, meaning that between the lines of force, there exists a force that makes them repel. So they form something like a loop between the North-South pole. So what happens when you place an identical poles together? Let's say South-South pole. What's going to happen? This is what we are going to look at. If magnetic field pattern due to two magnets are placed close together, then this is what we are going to observe. This is a case where we place two identical poles facing one another. In this case, we have the north pole. So what we note here is that we have repulsion, meaning that at that particular point, we are not going to have a force. There is no force. If you place a material there, then the material is not going to be attracted because the repulsion is coming from the two magnets since their identical poles are facing one another. And you know from the basic law of magnetism, like poles repel, so they are going to repel. So that point here is, that point that we have here is a neutral point. So we are not going to have magnetic force there. So the magnetic field around that particular point is zero. There is no force and therefore it's a neutral point for like poles which repel each other. So that one still helps to explain how the patterns look like when you place the magnetic field patterns due to a magnet of identical poles. Now, how does the magnetic field patterns look like when we use a horseshoe magnet or a U-shaped magnet? How will it look like? Magnetic field patterns due to U-shaped magnet, and we have one here. So that is the shape, how the magnetic field patterns is going to look like. Still, the magnetic field pattern is going to move from the north to the south pole, and then we say it forms a continuous loop. So we have an imagination that these field lines are still moving within the U-shaped magnet. But what is important here is not how the shape is, how the magnetic lines of force are moving from the north pole to the south pole, and in this case for a U-shaped magnet. That's how they are going to look like. Now, this basically gives us a description on how the magnetic field patterns of various materials look. For example, a bar magnet. We can also have a ring-shaped magnet. We have a horseshoe magnet, which is also known as a U-shaped magnet. When you draw the field patterns, one thing that you have to notice that the field lines will move from the north pole to the south pole all the time. And the lines of force never cross. They don't have to cross at any given point. So that's very, very important for us. So having gone through all this, I now believe that you have a lot of information that can help you attempt this as part of your assignment. So this is your assignment for the day. Explain the following terms. Magnetic field line, and we have just discussed that. Explain what you understand by magnetic field line. You also explain magnetic field pattern. That is question 1. Question 2, describe an experiment to explain the direction of the magnetic field line. Describe an experiment to explain the direction of the magnetic field line. Then question 3, draw magnetic field pattern due to two bar magnets placed, one side by side with the north and south poles near each other, then 2 with their south poles facing each other. So if you attempt all these 3 questions, then these questions will help you understand our discussions even better. Attempt this so that when we meet in our next lesson, we shall review the questions before we proceed to our next lesson. Up to there, I've been your teacher, Benjamin Makanda, and before we wrap the day, you can send your questions and comments on our SMS number 44407 or our Facebook page, LMTV. You can also follow us on Twitter at LMTV_KE. Stay tuned to LMTV. Till next time. Thank you.